I'm Takayuki Shizaki from Tokyo Institute of Technology. The title of this talk is Geometric Control Specification via Nyquist Surface Segmentation. As a motivating example, let's think about power systems control here. This figure shows a power network model called the IEEE 68 bus test power system. For the frequency regulation of this power system, a centralized control scheme called automatic generation control is often implemented. In this control, the average of frequency deviations is measured as an output signal from generators, while a generator control signal is broadcasted to controllable generators. Please note that both delta omega and U as you see here are supposed to be scalar signals. In general, a power system model is nonlinear, but we can linearize it at the operating point of interest. Then, the resultant linearized model, denoted by G theta, is dependent on some uncertain parameter theta. This parameter theta represents the distribution of uncertain loads. As you can imagine, the input-output property of the power system model can vary with the variation of the uncertain load parameter theta. This figure shows the Nyquist plot of the linearized power system model with 30 different load parameters. From this figure, we can see that if the load impedance increases, then the Nyquist curve of the linearized model expands. This means that the gain of the linearized model increases as the load increases. In fact, the set of such curves in the complex plane can be regarded as a surface. So we call this as the Nyquist surface of the model set, which is the collection of the uncertain models G theta. Here, let's consider the modeling of this uncertain system based on the expression of geometric domains. One possible way is to cover the Nyquist surface by a big disk like this. The radius of this big disk corresponds to the worst-case gain considering the variation of all load parameters. However, it is clear that such an expression is too conservative, as you can easily imagine from this figure. So, the key idea for a set-based modeling is to divide the entire Nyquist surface into several segments as like this figure. Here, we consider 5 disk segments denoted by D1, D2, D3, D4, D5. Each disk covers an oscillation mode of the power system. Please note that this segmentation of the Nyquist surface corresponds to the segmentation of the frequency range. Based on this segmentation idea, we define the notion of the geometric specification of model sets as like this. Let omega 1 to omega n be some frequency ranges. Then, a family of the geometric domains, denoted by script G, is said to be a geometric specification of a model set if the segments of its Nyquist surface are covered by the set of domains Di, which is associated with a compatible frequency range omega I. This is a mathematical rephrase of the figure in the previous slide. The main objective of this talk is as follows. For a given plant model set, which is specified by the geometric plant specification G, we aim at finding a geometric control specification denoted by K, which gives a specification of the controller model set. Here, the parameter phi represents some controller gains, for example. This objective is formally stated in this box. Please note that the internal stability of the feedback system here must be guaranteed for any pair of possible plants and controllers. Here, I explain the key idea to determine the geometric controller specification. As in the motivating example from the power systems control, we suppose that a geometric plant specification is given. In this figure, I only show two geometric domains denoted by D3 and D5 for simplicity of explanation. Because these different domains cover the Nyquist surfaces for different frequency ranges, we can decouple the analysis into those in the respective frequency ranges. Then, for each of the frequency ranges omega 3 and omega 5, we aim at finding a domain of controllers denoted here by D3 bar and D5 bar, such that the multiplication of D and D bar is equal to the green domains shown here. Please note that these green domains do not include the half-line L-1, so the Nyquist curve of the plant times controller does not encircle the point -1. As we can see here, the problem of finding a geometric controller specification can be formulated as the problem of finding a set of controller domains, shown here, that is compatible with the set of given plant domains, shown here. The idea in the previous slide can be stated as this lemma. In the first part here, we suppose that the plant model set satisfies a geometric specification denoted by script G here, and every plant model G theta is stable. This part simply states that a geometric plant specification is supposed to be given as shown in this figure. Please remind that the geometric plant specification is the set of domains Di associated with the frequency range omega I. Then, in the second part, we define the domain Di bar here such that the domain Di times Di bar is equal to the green domain here. This green domain can guarantee the internal stability of resultant feedback systems for all possible plants and controllers. Clearly, what we want to find is this domain Di bar corresponding to the domain of controllers. The final part here states that if the geometric controller specification K is given as a set of domains Di bar, and every controller K phi is stable, then the resultant feedback system is internally stable for any possible pair of plants and controllers. As we can see here, this statement seems complicated, but its meaning is clear. What we have to do is to find the domain Di bars for the given domains Di. As explained in the previous slides, the problem of finding a geometric controller specification can be reduced to a purely geometric problem to find a domain D bar for a given domain D. In the following, we omit the subscript I because the entire problem can be equivalently divided into the subproblems for respective frequency ranges. In particular, we suppose that the domain D of a plant is given as an open disk whose center is C and the radius is R as shown in this figure. Please note that the domain D bar can be written as an intersection of the parameterized domain D bar tau, like this. Then, substituting this relation into this inequality, which represents the point W being inside the given disk, we have a simple expression of the parameterized domain D bar tau like this. In fact, this domain in red represents also a disk called the circles of Apollonius. Based on the expressions of Apollonius circles, we can obtain the following theorem. Here, as in the upper subfigures, a given domain D is divided into the four cases depending on the location of the disk. And then, as in the lower subfigures, a compatible domain dbar is derived for each case. It is interesting to see that if the origin is involved inside the plant domains, like in the first and the second cases here, then the controller domains are also obtained as disks like this. Also, if the origin is on the boundary of the plant domain, like in the third case here, then the controller domain is obtained as a half plane like this. Finally, if the origin is outside of the plant domain, as in the fourth case here, then the controller domain is obtained as a domain outside the union of infinite many circles like this. This theorem gives the pair of plant and controller model sets such that their feedback systems become internally stable. Here, let's see the application example for power system models introduced in the beginning of this talk. As a simple example of a controller model set, we consider the set of PA controllers here. When we vary the controller gain in some range, the Nyquist surface of PA controllers is obtained as red boxes, as shown in these figures. Clearly, all the red boxes are inside the obtained domains, so we can prove that any combinations of plants and controllers are internally stable. This is the end of this talk. Thank you for your kind attention.